You've got 128 gigabytes of RAM. That sounds enormous. For most normal computer workloads, it is enormous. You can have dozens of browser tabs open, run virtual machines, edit 4K video, compile large projects, and still have memory left over. So naturally, if you get into local AI, you might think 128 gigabytes should let you run almost anything. And technically, in some cases, it can. But then you download a large language model, load it up, type your first prompt, and something feels wrong. The model runs, but it's painfully slow. Maybe you're getting 3 tokens per second. Maybe 1 token per second. Maybe you wait several seconds before the first word even appears. And suddenly that 128 gigabytes of RAM doesn't feel very powerful anymore. So what's going on? The problem is that when it comes to running large AI models, memory capacity is only one part of the equation. Having enough space to store a model does not mean your computer can move that model's data fast enough to run it efficiently. And for large language models, that difference is huge. Let me start with a very simple example. Imagine I have a 70 billion parameter model. If I run that model in 4-bit quantization, the raw weights might take somewhere around 35 to 45 gigabytes, depending on the format and quantization method. So if I have 128 gigabytes of system RAM, that model fits easily. I could even load something much larger. Maybe a 100B class model, maybe even larger, depending on quantization. So from a capacity perspective, everything looks great. But now we have to actually run the model. Every time the model generates a token, the computer has to perform a huge number of mathematical operations using those model weights. And this is where memory bandwidth becomes incredibly important. Think of RAM capacity as the size of a warehouse. Memory bandwidth is how quickly you can move boxes out of that warehouse. You can have the biggest warehouse in the world, but if the door is tiny and you can only move a few boxes every second, production is still going to be slow. This is exactly what happens with large language models. A typical desktop with DDR5 memory might have more than enough RAM capacity, but the bandwidth of that memory is nowhere near the bandwidth of modern GPU VRAM. A high-end GPU can have hundreds of gigabytes per second, or even more than a terabyte per second of memory bandwidth. System RAM can be dramatically slower. And for LLM inference, that difference matters because the model is constantly reading enormous amounts of weight data. This is why you can take the exact same model and get completely different performance depending on where those weights are stored. Put the whole model inside fast VRAM and you might get very responsive generation. Move most of it into normal system RAM and suddenly performance drops. The model didn't become less intelligent. The parameters didn't change. The only thing that changed was how quickly the hardware can feed data to the processor. And this is one of the biggest misunderstandings I see in local AI. People often ask, how much RAM do I need to run this model? Guide. But I think a better question is, how much memory bandwidth do I need to run this model at a speed I can actually tolerate? Because running and running well are two completely different things. Let's say I have a 70B 4-bit model that takes around 40 gigabytes. If it's running from system RAM, the computer may have to effectively stream a large portion of those weights through memory again and again as tokens are generated. So if your memory subsystem can only move data at a certain speed, that puts a hard limit on how fast inference can happen. You could install 256 gigabytes of RAM. It would give you more capacity. But if the memory bandwidth stays almost the same, your model may not become much faster at all. That's the key idea. More RAM does not automatically mean more AI performance. Sometimes it means you can load a bigger model, but the bigger model actually becomes slower. And now, another bottleneck enters the picture: compute. Even if memory bandwidth is good enough, the processor still has to perform the calculations. Large language models are basically giant stacks of matrix multiplications. GPUs are extremely good at this kind of parallel math. CPUs can do it too, but they're designed very differently. A CPU has a relatively small number of powerful, flexible cores. A GPU has thousands of smaller processing units designed to do lots of similar calculations in parallel. That's exactly the kind of workload AI models produce. So if you have 128 gigabytes of RAM paired with an ordinary desktop CPU, you may have enough memory to hold a very large model, but you don't necessarily have enough compute to process it quickly. This is why I always separate 3 things when I talk about local AI hardware: capacity, bandwidth, compute. Capacity tells me whether the model fits. Bandwidth tells me how quickly I can move the model's data. Compute tells me how quickly I can perform the math. And you need all 3 to get good performance. This also explains why unified memory systems can be so interesting for local AI. Take a high-memory Apple Silicon machine as an example. The CPU and GPU share the same physical memory pool. So if the machine has 128 gigabytes of unified memory, the GPU can potentially access a very large portion of that memory directly. You don't have this strict separation where the GPU only has, say, 16 or 24 gigabytes of dedicated VRAM and everything else has to sit in slower system RAM. But even here, capacity is still not everything. Different chips have very different memory bandwidth. Two Macs can both have 128 gigabytes of unified memory and still deliver very different AI inference performance. Why? Because one may have significantly more memory bandwidth and more GPU compute than the other. Same memory capacity. Very different experience. This is why I'm always careful when someone says, this machine has 128 gigabytes, so it should be great for AI. Maybe, but tell me the memory bandwidth. Tell me the GPU. Tell me the model. Tell me the quantization. Then we can actually estimate the performance. There's another thing that can eat into all that memory, the KB cache. When you run an LLM, the model isn't just storing its weights. It also has to keep track of information from the conversation or document it has already processed. That temporary memory is often called the KV cache, and the longer your context window becomes, the larger that cache can become. This matters a lot when people start using 32K, 64K, 128K, or even larger context windows. You may load a model perfectly fine at a short context length. Then you give it a massive document or an entire coding repository, and suddenly memory usage jumps. So 128 gigabytes might sound like a lot, but if you're running a very large model with a huge context, part of that memory is already spoken for before generation really gets going. And context doesn't just affect capacity. It can also affect speed. The model has more information to process, especially during the initial prompt processing stage. This is why you sometimes see a huge delay before the first token appears. That stage is often called prefill. If you paste a very long document into the model, the system has to process all those input tokens before it can start generating the answer. So if someone says, my model only generates 10 tokens per second, that's only part of the story. I also want to know time to first token. A model might generate reasonably fast once it starts, but take 20 seconds to begin because the initial prompt is enormous. That can make the whole system feel slow. Then there's quantization. Quantization is one of the main reasons we can run huge models on consumer hardware at all. Instead of storing model weights at 16-bit precision, we might use 8-bit, 6-bit, 5-bit, 4-bit, or even lower. This dramatically reduces memory requirements. But quantization also changes the way the hardware processes those weights. Some quantization formats are extremely optimized for certain GPUs or CPUs. Others are not. So two model files that are almost the same size can run at noticeably different speeds. This is why I don't choose a quantization purely based on file size. I care about the backend. I care about whether I'm using llama.cpf, MLX, TensorRT, XLLama, or something else. I care about whether that particular quantization is optimized for my hardware. Sometimes, a slightly larger quantization can actually run better because the software and hardware support it more efficiently. Another important issue is CPU offloading. Let's say I have a GPU with 24 gigabytes of VRAM, but my model needs 40 gigabytes. I can put as much of the model as possible onto the GPU and keep the rest in system RAM. That lets me run the model. And this is where 108 gigabytes of RAM can be extremely useful. Without that system memory, the model might not run at all. But again, there's a cost. Every layer that can't stay on the GPU may involve slower processing or more data movement between the CPU side and the GPU side. And depending on the software and the model architecture, this can absolutely destroy performance. So you may see someone online say, I'm running a 70B model on a 24 gigabyte GPU. That can be true. But I immediately want to ask, how many layers are on the GPU? How much is in RAM? What's the actual token speed? Because technically loading a model and comfortably using a model are not the same achievement. PCIe bandwidth can also become a bottleneck. The connection between your CPU, system memory, and discrete GPU is much slower than the GPU's own internal VRAM bandwidth. So if the workload constantly needs to move large amounts of data back and forth across PCIe, you're giving up one of the biggest advantages of the GPU in the first place. This is why the ideal situation for fast local inference is usually simple. Keep as much of the model as possible inside the fastest memory closest to the compute hardware. For a discrete GPU, that means VRAM. For a unified memory architecture, it means having enough high bandwidth shared memory available to the GPU. And this is also why a machine with only 24 gigabytes of VRAM can sometimes massively outperform a computer with 128 gigabytes of ordinary RAM. The 24 gigabyte machine may not be able to load as large a model, but the model it can load is sitting inside extremely fast memory, connected directly to a processor designed for massive parallel AI workloads. So maybe the 108 gigabyte machine runs a 70B model at a few tokens per second. The 24 gigabyte GPU runs a 32B model at several times that speed. Which machine is better? That depends on what I'm trying to do. If I absolutely need the larger model and I'm willing to wait, capacity wins. If I want an interactive assistant, coding model, or AI agent that needs to respond constantly, speed may matter more than parameter count. And that last part is becoming more important. When you're chatting with a model once, waiting a few extra seconds may not matter. But imagine an AI agent performing 50 model calls to finish one task. Now every second matters. A model that is twice as slow could make the entire workflow take twice as long. In that situation, I would often prefer a smaller model running entirely on the GPU over a huge model spilling into RAM. So when you see a computer advertised with 64, 28, or even 256 gigabytes of memory and you're thinking about local AI, don't stop at the capacity number. Look at the whole system. How much memory bandwidth does it have? What GPU or accelerator is actually doing the inference? How much compute performance does it have? Can the model fit completely inside fast memory? How much of it has to be offloaded? What context length are you using? What quantization format? And what inference software? Those details can matter more than doubling the amount of RAM. So yes, 128 gigabytes of memory is useful. Very useful, actually. It gives you the freedom to load models that smaller systems simply can't touch. But it doesn't magically make those models fast. Memory capacity determines how big the door is. Memory bandwidth determines how quickly data can get through it. And compute determines how quickly the work gets done once that data arrives. If one of those three is weak, the whole system slows down. That's why a computer with 128 gigabytes of RAM can still struggle with large AI models. The problem was never just whether the model could fit. The real question was whether the rest of the computer could keep up.